Hello my dear students, welcome to our channel Mr. Physics, where physics get charged. In the last video we have discussed the expression for electric field strength on the axial line of the electric dipole. So now in the today's video we will discuss the expression for E on equatorial line of the electric dipole. So what does mean by equatorial line here? The line passing through the center perpendicular to its length is called equatorial line, and this point is at the distance of r from the center of the dipole. Again, to write the net E at this point due to this dipole, we have the electric field strength at this point due to this positive charge as well as due to this negative charge. Let first I am taking the vector diagram of that E1 and E2 due to positive and negative charges, and then coming to write the magnitudes and proceeding for writing the expression for E, right? So this point P, so as it is a positive charge, due to this positive charge the expression for electric field is outward. Let this is a E1, okay, and we have the electric field strength at this point P due to this negative charge. This negative charge is having the electric field towards it, so that its electric field can be written as this side is towards the negative charge. So now here we can write the electric field strength at a P due to positive charge, due to plus Q charge, okay, we can write here E1 is equals to 1 by 4 pi epsilon naught into Q by, let this is a point A and here is a point B for our convenience, so that we can write a AP whole square, and it will be acts along this electric field is acts along AP only, means away from this A to the positive charge, right? And then what is the distance of AP, sir? So this is a A and it is a R, then definitely it is a right angle triangle, should be of R square plus A square, and that is the angle theta. So okay, so we will get the hypotenuse AP as adjacent side square plus height square, and similarly here also this is a A and R. At this side PB is also B of R square plus A square. Okay, so now we can write the expression for electric field strength. E1 is equals to 1 by 4 pi epsilon naught Q by AP square R square plus A square under root whole square. Square root get cancelled, so I'll get Q by R square plus A square. Let this is the equation 1. Similarly, now the electric field strength at a P again due to negative charge, due to this negative charge we can write as E2 is equals to 1 by 4 pi epsilon naught into Q by BP whole square. Again this BP is also B of R square plus A square under root, so we can write E2 is equals to 1 by 4 pi epsilon naught of Q upon R square plus A square under root whole square. Square root get cancelled. This is the equation 2, and this force, this electric field strength acts along P2B, along P2B. Why? Because towards the negative charge. So if you are observing their expressions of E1 and E2, okay, these two are equal in magnitude. When they are equal in magnitude, the resultant of the two can be obtained by angle bisector. When this is theta, here it should be theta. When it's a theta, here it should also be theta here. So now this E1 will be resolving into two components. One is of E1 cos theta, another is a E1 sin theta. Similarly, this E2 is also resolving into two components of E2 cos theta, and along this is a E2 sin theta. Means here when I am coming to the net electric field strength, the vertical component of electric field due to positive charge as well as due to negative charge, which are equal in magnitude but opposite in direction, so that they cancel each other. Means when coming to find the expression for resultant electric field strength at this point, the sum of these two, means sum of the horizontal components of electric field strength due to positive charge and negative charge is used the net electric field strength. So that therefore the net electric field strength at a P due to dipole can be obtained, okay, E net is nothing but E on equatorial line is E1 cos theta plus E2 cos theta. So you can take E1 common, and here E1 is 1 by 4 pi epsilon q by r square plus a square plus 1 by 4 pi epsilon q by r square plus a square into cos theta. So now and again, because of these two are equal in magnitude, so we can write E on equatorial line is equals to 1 by 4 pi epsilon 2 times of charge by r square plus a square into, from this cos theta, can I take triangle APO? So cos theta is equals to adjacent side is nothing but AO upon AP. Then this cos theta is equals to AO is a only, AP is under root of a square plus r square. Then can I write here cos theta value as a upon r square plus a square whole power 1 by 2. So therefore we will get here 1 by 4 pi epsilon 2a into q by r square plus a square whole power 1 plus half is a 3 by 2. And again, from the product of charge and separation between the two is gives a dipole moment we have discussed. So that here we can write E on equatorial line is equals to 1 by 4 pi epsilon of P by r square plus a square whole power 3 by 2. This is what the expression for the resultant electric field strength due to the dipole on its equatorial line. Now we are going to write the same in case of short dipole. In case of short dipole, A is very much less than R. So we have E on equatorial line is equals to 1 by 4 pi epsilon of P by, this is r square whole power 3 by 2. A is negligible as compared to R. So that here we will get E on equatorial line is equals to 1 by 4 pi epsilon into P by R cube. This is what the expression for electric field strength on the equatorial line here. If you remember, in the last video we derived the expression for E on axial line in the case of short dipole. We got 1 by 4 pi epsilon 2p by r cube. So by using these two, can I give the relation between E on axial line and equatorial line as 2 times of E on equatorial line is equals to E on axial line. Okay, so now my next point is the angle between, is important again, angle between P bar and E on equatorial line. So what is the E net on the equatorial line? By seeing this vector diagram, this is what is gives the E on equatorial line, which is along the rightward direction. And now coming to know the direction of dipole moment, the dipole moment direction is from negative to positive, so that the dipole moment will be in the leftward direction is a P bar. So therefore, by seeing this vector diagram, here we can give the angle between the P bar and equatorial line is 180 degrees, which means we can write E on equatorial line is anti-parallel to dipole moment direction. So this is the way we can write the expression for E on equatorial line due to short dipole as long dipole. It is similar to the again when you are taking in the magnetism, here it is the south pole and this is the north pole. It is the center, this called the equatorial line. So towards the south pole, away from the north pole is the E1 and the E2, and the same simplification here, and at last B on equatorial line we get by this is a mu naught by 4 pi capital M by r square plus L square whole power 3 by 2, because this is the length L and here is the length distance R. In the case of short dipole, B on equatorial line is equals to mu naught by 4 pi into M by R cube, like P by R cube, and here also B on axial line is equals to 2 times of B on equatorial line, and here also B on equatorial line is anti-parallel to dipole moment, magnetic dipole moment EM bar. These are the some comparisons of electric field strength due to dipole on an equatorial line and magnetic field strength due to magnetic dipole on equatorial line. Thank you for watching. If you like my videos, do like, share, comment, subscribe our channel to get more videos.